So first, I will give an introduction about the machine we are based on, the so-called Hipaa machine, and our goal. And then I will introduce you our first model. It's called the Recurrence Plot plus Convolutional Neural Network model. And then a second model, the Lasso model, which is much simpler and with another idea behind. And we are also going to introduce our evaluation metric of the beam time saved by those models. And in the end, I will also introduce some ongoing work around two-sample test. So first, I will going to introduce Hipaa. So Hipaa is so-called high-intensity proton accelerators, and it is cyclotron-based. So you can see two cyclotrons here. First, the proton beams are pre-accelerated to 870 keV here. And then in this injector 2, it gets accelerated again to 72 MeV, and we get the current of 2.2 milliampere. So after that, the beam gets finalized, so accelerated to its final energy, final kinetic energy in this ring cyclotron, which has 590 MeV and with the power of 1.4 megawatts. So this power actually makes Hipaa one of the most powerful proton accelerators in the whole world. And I'm not sure for now, maybe now it's not the best one, but so definitely one of the most powerful one. And after that, the beam gets delivered and separated into 7 different beam lines to different target stations. And so, for example, here you can see some experimental areas, doing some Gaussian experiments. And here is another single beam line. And also there are some other targets made by different materials for experiments. And in the work I'm going to show you today, we only focus on this core region of the whole facility. Yeah. And so because we really need to keep a close eye on such a complex machine, so there are actually a lot of monitors and sensors implanted into different places inside the machine. For example, we have temperature monitors, we have magnetic current monitors, we have beam position monitors, and so on. And all these are time series. And we also have a safety measure as the so-called interlock system, which actually monitors all these incoming signals. And once, if one of the signal gets above a safety limit, then an alarm will occur, which is a so-called interlock event. And then the beam will be shut off for safety, for safety reason. And this process of shut off the beam and then ramping up would cause about 25 seconds of beam time loss. And in the case of a severe problem, maybe some parts are broken, then this time would even be hours. So this actually, the beam time is the most important thing for our users in those experimental regions. So that's why we want to maybe predict if an interlock would come and then try to reduce this beam time loss. Yeah, so this is what we are trying to do. We try to have a forecasting model of the interlock. And once the model says there is going to be an interlock coming, we would try to do some recover operation on the machine so that the thing would be normal again and the interlock would be avoided. Okay, and so this is what we are going to do. We are going to forecast the so-called failure events, which are interlocks inside Hipaa. And our inputs are so-called channels, which are the signals from all the monitors of Hipaa. And we have in total 376 of them. And our target is the interlocks, which are the beam interruptions of Hipaa. So here I listed 3 different cases. of some example signals and interlock. And in this case, you can see that the bending magnet current is clearly increasing before the interlock happens, while the temperature also increases a bit. But this beam current at ring exit, it's just stable. And in the second case, the bending magnet current is actually decreasing before the interlock, while the other two are stable. And in the third case, both the three are somehow stable. So there's definitely information that we can extract in those signals, in those channels before interlock. But we really need to dig deeper into finding the relations that are actually strictly related to the interlock. Yeah, and in our first attempt, we try to formulate the problem as a binary classification of multivariate time series problem. So we have two classes. So the positive class is so-called interlock samples, which are taken close to the interlock, as you can see here. So we take the time windows very close to the interlock, only 1 second before. And the green ones are the negative class, which are the stable samples that are taken far away from the interlock. And this 10 minutes is a buffer region to take in between two adjacent interlocks to make sure that our stable windows are really inside a stable region. So if we look closer to one sample, we can see that this is a two-dimensional window with this dimension as our 376 channels. And this dimension is a time dimension of window length. And this window length is actually a tunable parameter inside our model training. So each row of this sample is a one-dimensional time series. Yeah, and as you can see, since interlocks are actually rare events along a very long timeline, we have highly imbalanced data set. So, so we try to balance the training set by overlapping and bootstrapping. But to still keep the imbalanced nature, we keep our test set still imbalanced, as you will see in the result. And now I'm going to introduce you how we treat our time series. So we use this method called recurrence plot, which can detect hidden dynamical patterns inside time series. So basically, a recurrence plot, they captures the recurrence of different values inside a time series. It transfers a one-dimensional time series into a two-dimensional image. And then since we have an image, we can use very highly developed convolutional neural network to exploit those information. So we choose the so-called global recurrence plot, which is a rather simple version of it. And it is just a distance matrix within the cutoff limit epsilon. And this epsilon is also a trainable parameter inside our model. So as you can see that Dij is just the distance between xi and xj, where I and j are just two timestamps inside our time series. And here I show you three examples of the recurrence plot. So the first one is rather uncorrelated stochastic time series. And the recurrence plot is like rather, yeah, so there's not much apparent patterns inside. And the second one is something starting to grow, and you can clearly see some patterns emerging here. And the third example is stochastic with a linear trend. So here you can see a lot of patterns growing, which are very different from the first one. Yeah, with that, if we feed those into a convolutional neural network, we can try to extract those patterns. Yeah, and then try to find the difference maybe hidden by just directly looking at the time series itself. And so now I will give you an overview of our RPCNN model, recurrence plot convolutional neural network model. So first, we take the two classes of multivariate time windows, and then we transform each of the one-dimensional time series to a two-dimensional recurrence plot, as shown here. And then we train these images with a convolutional neural network, and we get a binary output. So here I show an example output of 0.7, which means that we get a positive output with a classification threshold of 0.5. But we can also change the threshold. And if we have a higher threshold, we have like so we have a higher requirement for the thing to be positive and so on. So by changing the threshold and look at the output, this is the so-called meaning of the receiver operational curve, the ROC curve. And so this is the ROC curve, which is a curve of the binary output, binary classification problem. We plot the true positive rate against false positive rate. And so by analyzing our results, we also have defined a custom metric called beam time saved per interlock. And I will explain that in a second later. So basically, we assume this metric to reduce 10% of the beam current for 60 seconds once the model has reported a positive signal. And also in defining this metric, we have also considered to correct the imbalance of the two classes. So and these two numbers, 19 and 270, comes from expert knowledge of accelerator control experts, yeah, by considering these 2 points. And so here, now I will explain the result of the output and the ROC curve. So this is our confusing matrix, which is just a matrix that compares the samples which are actually interlock to be whether they are predicted as interlock or not. As you can see here, so we have 815 samples of actual interlock and so many samples of actual stable, so which are highly imbalanced. And why we and the reason why we choose to have a model with such a low true positive and also false positive is because of this ROC curve. So since we want to have the maximized beam time saved, so we want to have the maximized so this metric, and as you can see here, this metric actually punishes a lot on the false positive than increasing the true positive. So that's why we have this dashed line here. To the left of this dashed line, we only have the beam time saved larger than 0. So that's why we can only choose the points inside this triangular region. And if we zoom in here, we can see that this yellow dot means TS equals 0, and the blue dot means TS reaches max. And by having a dot here, it means that we have a very low false positive, but also we have also a very low true positive. Yeah. And so this is result shown in this table. So in the end, to suppress the false positive rate to only 0.2%, we have only also a very low true positive rate of 4.9%. And this is the model which makes our beam time saved the most. Yeah. Okay, and so the result before is actually only the results on the two different parts of the timeline. So which has the interlock samples very close to interlock and the stable samples very far from interlocks. And now what we are trying to do is having the incoming samples no matter where in time. And then for each incoming samples, we feed it into our forecasting model, and we will get an output also along with time. So this is the result you see here. We have the time in real case. So this is the result we take from a day in 2019. And so the orange lines are the actual beam current. And when the beam current drops to 0, it means that there's an interlock. And the blue line here is our model output. So as you can see here, the red circle I marked are those false positives, which means that the model output is higher than the threshold, and we don't really want them because this would lead to a lot of unwanted beam time loss. And in the second case, this is a true positive, so we successfully detect this interlock, but then here we still have a false positive. Yeah, so and based on some other analysis, we find that this RPCNN model, although it works, although it saves the beam time to 0.5 seconds per interlock, but the main problem of this model is that it has a lot of false positives, and we want to avoid that. So then we try to find a way to suppress the false positives. And also, we have also done some research on recurrent models. And those models also show that the changes are only happen at 0.2 seconds before the interlock. So based on all this past knowledge, we come up with another idea that we try to distinguish between only 0.2 seconds before the interlock and 0.4 seconds before the interlock. So we mark 0.2 seconds as the class positive and 0.4 seconds as the class negative. And then this becomes, again, a binary classification problem, but much simpler, because then in this case, all these inputs are not a time window, but only the vector at one timestamp. Yeah, so here we still have a binary classification problem with the input x with n input, and each input sample is a vector of 376 channels. And our output for this 0.2 seconds, the positive class, is labeled as positive, and our output for the negative class, 0.4 seconds, is marked as negative. And so now I'm going to introduce you this Lasso model. So which is just to add a regularization term onto a linear regression model. So as we have this kind of input and this kind of binary output, we want to fit and train a weight omega, which is also a vector in d dimension. And Lasso is so-called least absolute shrinkage and selection operator. The meaning of Lasso is that we have this loss function L, which have two components. The first term is the standard logistic loss for a binary problem. And the second term is the so-called regularization term, which is L1 norm. And that is the meaning of this least absolute shrinkage. So to try to explain Lasso a bit, it's like, so this red circles are your original loss. So, and then this black lines, the black contours are those regularization loss. And if we move towards this direction here, if we reach such a point here, we make our original loss decrease, but such a point would actually lead to a larger contour of our regularization loss. So in the end, we would most likely reduce to a point here, which means that the weight has some component to be suppressed to 0. And in this sense, we can actually select features because we can actually see that for each feature, whether the weight according to this feature has been suppressed to 0 or not by the model. Yeah, and so Lasso actually encourage a model to be simple and sparse. And by having a sparse model, we can actually increase the interpretability of our model in the sense that we can see that which input channels are more important according to the weight. And this lambda here is the regularization parameter. With a larger lambda, it means that more input features will be suppressed to 0. So if we apply to so if we apply this lasso to our model, we can see that so in this positive samples with y to be +1, we would try to make the omega times x to be positive, as we want to minimize the loss here. So then try to minimize this loss term means that we really need to make this part positive so that the whole thing can be very small. Yeah, so in this sense, for a positive sample, we want to train the weight to make the multiplication to be positive. And for a negative sample, we want to make the weight so that the weight times input to be negative. And with the Lasso model, we achieve in the end 124 input channels with non-zero weights. So in the end, we are left with only 1/3 of the whole channels in the beginning. And this is the confusion matrix of our Lasso model. So you can see that it actually performs very, very good. Yeah, so we can successfully say that, yeah, maybe there's really significant difference between the data 0.2 seconds before the interlock and the data 0.4 seconds before the interlock. And now I'm going to introduce you our new beam time saved metric in a continuous case. So as I've also said before, we have assumed that we have an operating window so that once our model output cross the threshold, which means that our model tells us that, okay, there's gonna be an interlock coming, we would then immediately reduce the beam current by 10% for t seconds. So this is shown here as such a window with t seconds. And so in this sense, by doing such an operation, we would lose t over 10 seconds by doing that. And instead of 25 seconds of an interlock. So by doing such an operation, we would actually save 25 minus t over 10 seconds. And if we have a false positive, the meaning is that, so by looking at the prediction, if the prediction is above the threshold, which means that the model tells us, okay, there's gonna be an interlock, we start to reduce the beam current by 10%, but actually there is not an interlock. So this is a false positive. And in this sense, we would just lose t over 10 seconds. Yeah. So by taking all this into account, we can come up with this beam time saved in any given time range. So we have the knowledge that an interlock would lose 25 seconds of beam time. And if we if the model predicts there is going to be an interlock, we would have an operating window which loses t over 10 seconds. So in this sense, if we have a true positive, before we take the operation, we would lose 25 seconds. And after the operation, we would lose t over 10 seconds instead. So in the end, we actually saved 25 minus t over 10 seconds. And for a false positive, which means that there's actually no interlock, but the model predicts an interlock will happen. So before we do this operation, we would lose no beam time. So there will be everything normal. But after we do this operation, we would actually lose t over 10 seconds. So in the end, we would lose t over 10 seconds. And for true negative and false negative, nothing would going to change. So in the end, we would have beam time saved in any given time defined as the number of true positives times 25 minus t over 10, and then minus the number of false positive times t over 10. So this is our beam time saved in a continuous case, which is depend on the length of our operating window t, and it is also actually depend on the classification threshold we defined, because this actually defines the number of true positive and false positive. So this is actually a real output as shown here. So the yellow curve are the beam current, and the blue dots are our model output, model prediction. And you can see that the green region is marked, is the true positives that are marked here. So we successfully predict an interlock going to happen. Yeah, and then so this part and this part, since the model output is above our threshold, but actually there's no interlock happening, we are going to have two false positives. Okay, and now with our newly defined beam time saved metric, we can compare the two models. So for the Lasso model, we can see that actually we have, so in this day, so October the 6th in 2019, in this day, there are totally 23 interlocks, and we try to have an operating window of 60 seconds. So we can see that for the Lasso, it actually successfully detects all of the 23 interlocks. So we have true positive of 23 and no false negatives. And apart from that, we also have 14 false positives that are shown in the yellow region here. Yeah, so in the end, we would have saved 353 seconds in the whole day. And if we divide by the number of interlocks, we would save 15.3 seconds per interlock, compared to only 0.5 seconds before in the other metric in RPCNN. And for the RPCNN, also in the same day, it only captures 7 of the 23 interlocks, which means that we have 16 false negatives. And also it has a lot of false positives. So in the end, we have 52 false positives in the whole day. So we actually lose 179 seconds in the whole day by using an RPCNN model. Yeah, so this actually shows that a rather simple Lasso model actually performs better than the very complex RPCNN model before in this continuous sense. And now we are trying to actually look into the difference between 0.2 seconds and 0.4 seconds before the interlock. Since we have observed that the Lasso model performs so good, we really want to see if there's statistically significant differences between 0.2 seconds versus 0.4 seconds before interlocks. And this is why we try to use the method called two-sample test from statistics. So to introduce you a bit about two-sample test, so we have the samples X and Y that are following the distribution of P and Q. And we want to do this hypothesis testing of H0 is that P and Q are actually identical distribution. And our so against the hypothesis H1 that P and Q are actually different distributions. And how do we do that? We define a test statistics lambda n calculated from the data X and Y. And we can, so the lambda n can be simply understood as a distance measure of X and Y. And I think, so that's actually easy to understand that, so if X and Y are from the same distribution, their distance should be somehow close to each other. And if X and Y are really from different distributions, the distance of X and Y should be large somehow. Yeah, so if our test statistics lambda n exceeds a predefined threshold, we would reject H0, which means that they are from different distribution. And how do we define this threshold? The threshold is actually the alpha quantile of the distribution of lambda n under the hypothesis H0. And alpha is our confidence. So for example, alpha can be 0.01, yeah, and so on. And so here is actually a sketch of the thing. And so this is the distribution of lambda n density under the hypothesis H0. Which means that X and Y are from the same distribution. So if we say that the threshold is taken here, so if we say that maybe the 1 minus, so yeah, if the 99% confidence threshold is taken here, which means that lambda n is equal to 0.07, then if we calculate our real lambda n from the data, and then if our real lambda n is larger than 0.07, this is very, very unlikely to happen under H0. But this is actually very, very easily to happen under the hypothesis H1. Yeah. And so here are some preliminary results of the two-sample test between different time before interlock. So we take our alpha to be 0.01. And here is like the test of two group of data from 0.2 versus 0.2, which has to be the same. And it is actually also the same with our test statistics lambda n to have the value of 1.2. And this is the result of 0.2 versus 0.4 seconds, which are identified as different. And you can see that we have a very, very large lambda n here, which means that they are really from the different distribution. And if we go along further in the past to test 0.2 seconds versus 0.6 and 0.8, we see that our test statistics increase more, so that we can really confidently say that 0.2 seconds data is really different than all the others. And by looking at 0.4 versus 0.6 and 0.8, it is actually also identified as different by the statistics. But if we look at our test, so if we look at this lambda n, the value is actually quite low compared to the one in the 0.2 case. So we can actually say that 0.4 seconds before interlock is not much different from the others, but still a little bit different. And then if we look at 0.6, 0.8, and also further in the past, they are always considered as the same distribution with a very low test statistics. Yeah, so by the result here, it actually confirms our Lasso model to only look at the difference, the two different samples taken at 0.2 seconds and also 0.4 seconds before the interlock. And so now I'm going to conclude and maybe have some outlook of the further work. So we have formulated a forecasting problem into binary classification problem. And also the RPCNN model transforms a time series into images and extract patterns. And also we save 0.5 seconds of beam time per interlock. And then we also introduce a Lasso model, which suppresses the false positives. And we can save up to 5 minutes of beam time per day, and also 15 seconds of beam time per interlock with our newly defined continuous metric. And also from the preliminary result of the two-sample test, we can conclude that beam interruptions are more of an abrupt events rather than gradual buildups. But these are actually, we are still looking into that. And yeah, so here actually there should be a question mark. And we are also going to do some further experiments on whether our operating window, so whether reducing the beam current by 10% could actually avoid the interlocks. So with that, I'd like to conclude my talk. And so here are those references I use. And I would especially thank Melissa Zacharias, who did the master thesis of the same project as along with me. And those recurrent plot methods are a lot part are coming from her idea. So special thanks to Melissa.